today we will be discussing what are uniformly continuous functions. So far we were discussing what are continuous functions on closed bounded intervals and so on. In this session we will be discussing uniformly continuous functions. So what is the major difference between continuous functions and uniformly continuous functions? So first let us have a quick insight to what are continuous and uniformly continuous functions, and then we will look at the proper definition. So continuous functions, as discussed in the previous classes, were functions which have their limiting value exactly equal to the value of the function. But in the case of uniformly continuous functions, we are giving some more restrictions to the functions, namely the function should have or should be equal to the value of the function, but that should not depend upon the value of the x or depend upon the x values in the domain of the function. For every value the function should be exactly in a same pace or in a same regular variation should be there. So for example, we can consider the function, say f of x is equal to 1 by x given in the interval x belongs to open interval 0 1. So if you look at this function, say f of x is equal to 1 by x, x is given to be in the open interval 0 1 means x is never assuming the value 0 here, because 0 is not included. But when we look at the function f of x, we can have a graph something like this. The function f of x is equal to 1 by x given in this interval. So it is something going like this. This is the value 1 corresponding to 1. I am not considering the scaling here. You suppose that that is the point 1 1. So looking at this interval, we can see that in this interval the function is continuous, because at each and every point we can see that the value of the function and the limiting value are exactly the same. But when we consider the points near this 0, we can see that the interval, if we are taking a particular interval here, say c minus delta, c plus delta, the variation in the corresponding values of the function is this much. Whereas if we consider an interval of the same width here, say this is your c minus delta, c plus delta, the corresponding variation is much larger. That is because of the point that we are considering. Again, if we come close to 0, we can see that for a very small change itself, the value of the function is having a very high difference compared to exactly same difference for the corresponding x values. So there are some continuous functions which are of this nature. The corresponding neighborhood of x will have the same delta value for different neighborhood of x values, for different x values will show a very wide variation for the corresponding function values. So for uniform continuity, it should not occur. For uniform continuity, whatever be the point that we are choosing, this variation should be uniform. The variations of the corresponding function values should be uniform. So that is the concept of uniform function or uniform continuity, and with that insight we can look at the definition of uniformly continuous function. Let A be a subset of R and f is a function from A to R. F is uniformly continuous on A if for each epsilon greater than 0 there exists a delta epsilon greater than 0 such that if x and y belongs to A satisfies the condition 0 less than modulus of x minus y less than delta epsilon, f of x minus f of y is less than epsilon. So, there is only a slight difference in the definitions of continuity and uniform continuity. In the case of continuity, we had defined continuity at a point, whereas in the case of uniform continuity, the points are irrelevant. That is why we are taking for any two points x and y which satisfies the condition 0 less than modulus of x minus y less than this delta, modulus of f of x minus f of y should be less than epsilon. So, whatever be the x and y values, wherever we are taking the interval in the domain, the corresponding function value should have the same variation. So, that is exactly what is said in the definition of uniformly continuous function, and that is the reason why we are writing like this. For each epsilon greater than 0, there exists a delta of epsilon greater than 0. So, look at this delta, it is given to be delta of epsilon, which emphasizes that this delta depends only on the epsilon value and not on the x or y values that are chosen. So, that is the definition of uniform continuous functions. Now, as an example, we can see f of x is equal to 1 by x is uniformly continuous on some a to infinity where a is strictly greater than 0, because just now we have seen that example 1 by x is continuous on the interval 0 to infinity or 0 to 1 or whatever it be, but it is not uniformly continuous as we become closer and closer to 0. But we can say that this is uniformly continuous on some point a to infinity. So, let us look at the proof of this based on the definition. What was uniform continuity? Given epsilon greater than 0, we should be able to find out a delta greater than 0 such that modulus of f of x minus f of y should be strictly less than epsilon for every x and y in A or in the domain for which modulus of x minus y is less than delta. So, this was the condition that we had to prove. So, we are given the function f of x to be 1 by x, and we are given the condition that the domain A is equal to a to infinity. So, f of x is equal to 1 by x and f of y is equal to 1 by y. Therefore, modulus of f of x minus f of y becomes modulus of f of x minus f of y is equal to modulus of 1 by x minus 1 by y, and taking the LCM, we will be getting it is equal to modulus of y minus x upon xy, and we can see that this a is strictly from a to infinity, and so x and y are less than or equal to a, and therefore we can replace this modulus of y minus x by this is less than or equal to modulus of x plus modulus of y upon 1 by xy. So, that is strictly less than modulus of a plus modulus of a, and that is less than twice modulus of a, and so we can have a particular delta corresponding to depending on a, because we are having x and y values from a to infinity. And therefore, whenever modulus of x minus y is less than that value, correspondingly modulus of f of x minus f of y will be less than epsilon, which completes the proof of this result, saying that f of x is uniformly continuous on closed interval a to open interval infinity. An exactly similar result can be seen for f of x is equal to 1 upon x square, and this also can be proved to be uniformly continuous on closed interval 1 to infinity, but not on 0 to infinity. because it is given to be 1 by x square. Exactly similar condition holds if we omit the portion containing 0, because as we become more and more closer to 0, there the variation becomes much more larger. So we can have it is uniformly continuous on 1 to infinity, but not on open interval 0 to infinity. So that is another example which can also be proved in a similar manner. And we can have many more examples like sin x square, for example, or simply the function f of x is equal to x square on closed interval 0 to 1 is uniformly continuous, and so on. Many functions are there which can be easily proved to be uniformly continuous, and many functions which can be proved to be continuous only but not uniformly continuous if we restrict the domain. So again, taking this example, for example, if we are taking f of x is equal to x square, we can see corresponding to epsilon greater than 0, we need to find a delta greater than 0, for which modulus of f of x minus f of y is less than epsilon whenever modulus of x minus y is less than delta. So we can start with your x square minus y square, which is exactly equal to x minus y into x plus y, and this interval is given to be closed interval 0 1. So definitely x and y belongs to the closed interval 0 1. So x and y are both less than or equal to 1. So applying the triangle inequality, we get mod x plus mod y into modulus of x minus y, and that is equal to, or that is less than or equal to twice modulus of x minus y. So we have to satisfy the condition that given epsilon greater than 0, definitely there exists a delta which depends only on epsilon, for which this condition holds. So taking that, we can have modulus of x square minus y square is less than epsilon whenever 2 into modulus of x minus y less than epsilon, by considering the condition that just now we have proved. So this indicates that that is modulus of x minus y less than epsilon by 2. Therefore, our choice of delta will be a real number. Delta will be any real number less than epsilon by 2. So if delta is any real number less than epsilon by 2, whenever modulus of x minus y is less than delta, modulus of x minus y becomes less than epsilon by 2, and so 2 into modulus of x minus y becomes less than epsilon, which forces our modulus of x square minus y square also to be less than epsilon, which is exactly required for showing that f of x is equal to x square is uniformly continuous on closed interval 0 1. So that is how we prove the uniform continuous functions. So these are some of the examples that we have seen. Now looking at a very important result which indicates that when is a continuous function surely uniformly continuous. When can we say that a continuous function is definitely uniformly continuous? So if I is a closed bounded interval, and if f is a function defined from I to R is continuous on I, then f is uniformly continuous on I, because just now we have seen, that is why I have shown this example for you, because f of x is equal to x square we had taken on the interval 0 to 1. So what happens if we do not restrict the domain to this interval? Because it was restricted to this interval 0 to 1, we could apply modulus of x plus y is less than or equal to 2. We were able to apply this result here because of this condition given. Otherwise, for the entire real numbers, if we are not restricting the domain to the closed interval 0 1, instead we are opening the domain to be the entire real line, we cannot have a value like this here, because we cannot have an upper bound for mod x and mod y. In that case, we cannot have this function f of x is equal to x square to be uniformly continuous. So, this has to play some role to show that the function is uniformly continuous, and hence we restrict the domain to be closed and bounded interval, and f should be continuous. Then only f is clearly uniformly continuous, we can say. Okay. So, the proof goes like this. So, the proof of uniform continuity theorem goes like this. Given f is continuous on a closed bounded interval, say AB. So, we have been learning many theorems regarding continuous functions on closed and bounded intervals, and so f is continuous on closed bounded interval means indicates that f is bounded, f of I is strictly contained in small m capital M, and we have learnt the Bolzano's intermediate value theorem as well. So, using these conditions, we are going to show that f is uniformly continuous on the interval I. So, before going to the proof of uniform continuity of uniform continuity of f, we can see some non-uniform continuity criteria. Non-uniform continuity criteria. That means, when will you say that the function is not uniformly continuous? So, uniform continuity shows that given epsilon greater than 0, there should exist a delta greater than 0 such that modulus of x minus y less than delta indicates that modulus of f of x minus f of y less than epsilon. So, non-uniform continuity criteria says that given any epsilon naught greater than 0, we should be able to find a delta greater than 0 such that, or for every delta greater than 0, that is the exact negation. For every delta greater than 0 such that modulus of x minus y less than delta forces modulus of f of x minus f of y is greater than epsilon naught, or in particular we should find there exists some point x delta y delta such that in the domain A such that x at least one point satisfies this condition, then it is not uniformly continuous. The second condition is that given epsilon naught greater than 0, for every natural number n, we can find a sequence xn and sequence yn such that modulus of xn minus yn is less than say 1 by n, but modulus of f of xn minus f of yn is greater than epsilon naught. So, these two are the non-uniform continuity criteria which forces a function to be non-uniformly continuous. So, given epsilon naught greater than 0, either we should be able to find out at least 2 points corresponding to every delta for which this condition holds, or for every natural number we should be able to find out 2 sequences which shows that modulus of f of xn minus f of yn is greater than epsilon naught whenever modulus of xn minus yn is less than 1 by n. So, using one of these conditions we are going to prove this. So, we need to show that to prove that f is uniformly continuous, If possible, let us suppose that f is not uniformly continuous. If possible, we will assume that f is not uniformly continuous, but f is defined on a closed bounded interval and it is continuous. Then by the condition number 2 of non-uniform continuity criteria that we have seen just now, there exist two sequences un and yn or xn and yn such that whenever modulus of xn minus yn is less than say delta or 1 by n or whatever it be, this forces your f of xn minus f of yn to be greater than epsilon naught. So that is the non-uniform continuity criteria that we are applying here. So we have two sequences xn and yn in I, because I is the domain. And what about I? I is a closed bounded interval. So sequence xn is bounded and hence by Bolzano-Weierstrass theorem that we have seen in many of the previous sessions, Bolzano-Weierstrass theorem, there exists a sequence xnr, or we can rename another, we can give another name for this, say okay, sequence xnr is okay, say sequence xnr which converges to some number, say z. And because I is closed indicates that z belongs to I, because in a closed set contains all its limit points, and so z belongs to I. And sequence xn and sequence yn are such that modulus of xn minus yn is less than delta. In particular, we can write less than 1 by n. So these two sequences are Cauchy, we can say. They are very close to each other. So xnr is a subsequence of xn, and correspondingly we can have a sequence ynr such that modulus of xnr minus ynr is less than 1 by nr, and since xnr converges to z, consider modulus of z minus ynr, insert your xnr in between. So this is equal to modulus of z minus xnr plus xnr minus ynr, and that is less than modulus of z minus xnr plus 1 by nr, and as nr tends to infinity, this value 1 by nr goes to 0, which forces your z minus modulus of z minus ynr should be less than modulus of z minus xnr, and since xnr converges to z as n tends to infinity, this forces ynr also goes to z as n tends to infinity. Limit nr tends to infinity, ynr is also equal to z. So we have modulus of xnr minus ynr to be less than 1 by nr, that is very small, and xnr goes to z, ynr goes to z, and by the continuity of f, this forces, these two forces what? F of xnr goes to f of z as nr tends to infinity, and f of ynr goes to f of z as nr tends to infinity, and therefore f of xnr minus f of ynr goes to 0 as nr goes to infinity. So this sequence, actually it is a sequence of real numbers, right? Because everything is a real number. F of xnr is a real sequence. F of ynr is a sequence of real numbers. So actually the difference between these two is also a sequence of real numbers which goes to 0. But our previous assumption was that, where is that assumption? Xn minus yn is less than 1 by n forces your f of xn minus f of yn to be greater than epsilon naught. So we have f of xnr minus f of ynr to be greater than epsilon naught, but now we have seen that it is actually converging to 0. So this contradicts, which contradicts the fact that modulus of f of xnr minus f of ynr is greater than epsilon naught. So that is a contradiction. Hence our assumption is wrong. Therefore our assumption is wrong. We cannot have f to be non-uniformly continuous, which forces our function f to be uniformly continuous. So remember that for the theorem of proving uniform continuity, we required many of the previous theorems that we had learned. So that is a peculiarity of real analysis. Every theorem needs one or two of the previous results that we had learned so far. So there should be a continuity for a clear understanding of each and every theorem that we are learning in real analysis. So that you have to keep in mind. So this is regarding uniformly continuous functions. In the next session also we will be discussing some more properties on uniformly continuous functions. That is all for today. Thank you.